Hello, my name is Erin King. I'm a PhD student at the University of Plymouth with the Coastal Processes Research Group, and today I'm giving a presentation on what controls headland sand bypassing. So, embayed beaches make up around 50% of global shorelines. Now here's an example of a chain of embayed beaches along the north coast of Cornwall, between Perranporth and Newquay. It's important to know the sources and sinks of sand, of sediment, into these bays to understand the sediment budget and the coastal evolution in the long term. Sand can move around headlands, highlighted here in orange, under wave and tidal forcing in a process that we were calling headland bypassing. Now, bypassing can be predicted for idealized headlands, and this is from a paper which is currently under review by Jack McCarroll in Coastal Engineering, shown at the in the text below here. And it can be predicted for idealized morphologies along open stretches of coast, but it remains to test this kind of parameterization in a range of real headland morphologies, chains of embayments, and also to quantify the influence of waves, tides, and wave current interactions. So to do this, we used the southwest UK as a test site. We looked at 75 kilometres of embayed coast and 29 headlands numbered here along the stretch of coast. We created a three-dimensional coupled hydrodynamic and wave model using Depth 3D. That's shown, the domain is shown here. We nested this regional model within a, we nested the three-dimensional North Coast model within a regional model shown here, which had a 1 kilometre resolution and was used to give water levels and currents to the more refined model's boundaries in the red lines here. The model had a 50-metre resolution on the headlands. So here's an example of the model grid at Godrevy Point. And you can see that the resolution is fine enough to well resolve the morphology of that headland. Sand transport was calculated using the Transport 2004 formulation of Van Rijn. And the model was calibrated using ADCP deployments at the wave hub, and then validated at wave buoy deployments at the wave hub and at Perranporth, and also ADCP deployments off the Perranporth North Headland. Here's an example of the wave validation at Perranporth. So we see going from top to bottom, we have the significant wave height, the peak period, and the direction. In blue is the model, and in grey is the observation. And on the right-hand side, we have an XY plot, and black is the perfect agreement 1-1 line. So we want our points to follow along that line. Model is on the y-axis, and the buoy is on the x. So we see the buoy, the model is doing pretty well. It's capturing all of the peaks in the significant wave height. It's capturing the variation in the period and direction well. Periods where the significant wave height at the buoy was less than 1 metre are shaded here in grey, and also in these plots. And you see that the times where there is disagreement between the model and the buoy, you can see that they're related to periods where the wave height was quite low at the buoy. So it's doing well for energetic conditions, which are the main forcing conditions for headland bypassing, as we will see. So the currents now at A17 is more near shore at Perranporth North Headland, and A25 is further offshore. And then we also have the A25 but at the bed to show the how the model performs near the bed. Again, the tidal signal between the model and the observation, that's doing quite well. They're both lying on top of each other, and that's reflected in the XY plot here with the gray points. And then we also have a harmonic analysis was performed, and the harmonic tide was subtracted, relieving the residual. That's on the y-axis to the right. So we see 20 centimeter per second residual current, sort of maximum residual current. And the model is in red, is predicting that pretty well in all cases. 9 scenarios were tested. We had tested for waves only at different water levels, tides only, and waves and tides. So 9 wave scenarios: medium waves, 50% exceedance, large waves at 5% exceedance, and extreme waves at 12-hour exceedance from 3 different directions, gives the 9 wave scenarios. There are 2 water levels, spring high and spring low water, and with and without tidal currents, giving 36 forcing scenarios. These were also performed for uniform sediment coverage, so sand cover everywhere, and spatially variable sediment coverage, so not considering sediment depth, but considering the spatial availability of sediment, so which areas have sediment, which areas are bare rock. And that gave 72 scenarios in total. Now the sediment coverage was inferred from high resolution UKH obathymetry shown in plot 1 here. Subtracted a median filtered surface from that and a 100-meter window, which gives what you see in plot 2. Then we did the maximum standard deviation of that same window, which shows plot 3. And you can see the rock is fairly well defined here, and that was able to be used to distinguish areas of sand within the embayment, leading to plot 4. And this was done all across that 75-kilometer stretch of coast. Headland morphology was quantified for an upcoast and a downcoast morphology relative to the bay. So here we have the upcoast in red and the downcoast in black. The apparent morphology, so we're going to talk about apparent morphology here, is the morphology of the headland at that particular water level, and it changes with water level. So this here is spring high water. Now the headland morphology is defined at the waterline. So when we go to spring low water, the headland morphology will change as that waterline changes. And that's important for predicting headland bypassing rates, as we'll see later. Now, we've quantified a number of morphometric parameters. I'll go through some of the main ones here. So the cross-shore headland extent, if you extend a line from the back beach out through the headland and then go perpendicular to that from that to the headland apex, you get the length there is the headland cross-shore extent excess. We have the surface zone width perpendicular to the beach here, SW. We have the breaking wave height and breaking wave angle here. We also have the depth of the headland toe, ZT, and QB is the bypassing rate. Some other parameters which were used but weren't found to be significant were the length of the back beach and the area of sediment coverage, so sediment here in purple, the area of that coverage relative to the area of the depth of closure, but that wasn't found to be particularly relevant. So cross-shore headland extent was found to be smaller up coast than down coast. Here is for spring low water in blue and spring high water in red. And we see the up coast morphology in dark blue there tended to be less than the down coast morphology. Same here, up coast in light red tended to be smaller than the down coast, with more variability in the down coast morphology as well. So this might predispose the section of coast towards up coast bypassing, so bypassing to the northeast. Bypassing rates, QB, were strongly dependent on the ratio between the headland cross-shore extent and the surface zone width. So how far does the headland extend offshore relative to the width of the surface zone? there was very little bypassing. So on this plot here, the colors are the bypass rate. We have the log-E scale with the ratio excess over surface area width on the x-axis. Y-axis we have the breaking wave angle, and we see very little bypassing when the headland is more than 5 surface area widths in length across shore, and we have greater bypassing when you have a smaller headland relative to the surface area width. Now, at spring low water, we see between a factor 2 and a factor 3 increase in the bypassing rate relative to spring high water. So this is bypassing at spring low over bypassing at spring high. For large and extreme waves, we see that between factor 3 and a factor 2 increase. But for medium waves, we see a much larger relative change and a greater spread as well. But that can all be accounted for by changes to that apparent morphology, as discussed before. So the parameter presented by Maccaro et al. Is shown just below here. So QB is equal to the Q naught, which is the uninhibited longshore flux, so the amount of sand transport longshore, or the transport rate longshore, where there would be no headland present. And then that is multiplied by this factor here, which is an exponential term of the cross-shore extent of the headland relative to the surface zone to the power of a factor. And this to the power of an exponent even. So this exponent has been adjusted slightly, that's why we're calling it QB adjusted. It's a minor adjustment though, and that the performance of that equation is shown here. So on the y-axis we have the parameterization, and on the x-axis we have the model. And we see it's doing fairly well. It's getting the order of magnitude, but there is still some spread that we're seeing here. So we want to see if we can improve that. So the first thing to check is the headland toe depth. So here we have a set T, 50 meters off the headland toe. We then divided that by 50 meters to give a ratio with just taking the dimensionality out of it really, which is the MT parameter here. So if we have that same plot from before, but now colored with this MT parameter, we see that for headlands with a deep deep headland toe, so the headland drops off quite steeply at the headland toe, at the headland apex, then we have the parameter QB is over predicting the bypass rate, whereas when it's quite shallow off the headland toe, it is under predicting the bypass rate. So we've introduced this new correction here. So this is that QB adjusted from before, and then we're adding another exponential term here, which is A and B are fitting parameters, and then MT here is our MT parameter there. And we see that it brings the MAE, the mean absolute error, down to within a factor 4. And we see that it's doing fairly well. It's able to capture the magnitude of headland bypassing quite well. This is for uniform sediments in wave-dominated conditions. So what happens when we have non-uniform sediments? What happens when there's no sand present, if there's areas of bare rock, for example, off the headland apex? So here is an example of that. So these headlands have no sediment off the headland apex. So we found that when there is sediment off the headland apex, so if this purple area covered that headland apex, headland toe, then QB toe is sufficient under wave-dominated conditions to predict the magnitude of bypassing. But when there isn't sediment there, then a correction factor needs to be applied. And this is QB sed is so bypassing with variable sediment is an order of magnitude less, so 0.1 times QB2. Now this only applies A, when there's no sand off the headland, but also it only applies when the cross-shore extent of the headland is greater than half a surface zone width from the outer edge of the surface zone. So excess is greater than 1.5 surface zone widths. This is shown here. So we have in red where those two conditions are met, and in blue are where there is no sediment off the headland toe, but the headland itself is quite small relative to the surface zone width, less than 1.5 surface zone widths across. And we see that QB2 actually does fairly well in these cases. However, where excess is greater than 1.5 surface zone widths, we need to apply the correction factor. And once that's applied, it brings the RMSE, root mean square error, down from a factor 10 to a factor 7.6, and brings the mean absolute error to within a factor of 5. So again, we're able to get the order of magnitude of bypassing fairly well. Now these are all wave only parameterizations. So for wave dominated conditions, we want to know when can this be applied? What is the applicability of this kind of parameterization based on wave dominated conditions? So the relative dominance of waves and tides was tested using the classification scheme from the first chapter of my PhD, which is published here. And this scheme goes like this. So we have two ratios. First ratio is bypassing, in this case, headland bypassing for a tide only scenario relative to the headland bypassing in a wave and tide scenario, and you subtract the tide only signal from that. So that's essentially the tide only bypassing relative to the effect of waves as well as nonlinear interactions. Now, the second ratio, so the first ratio is along here on the sort of y-axis. Second ratio is the bypassing for a wave-only simulation relative to the influence of nonlinear interactions. And that influence of nonlinear interactions can be determined by taking the wave and tide scenario, subtracting the bypassing from a tide-only and a wave-only scenario from that. So you're taking out the tide and the wave component and just leaving the contribution from that wave current interaction there. And that's on the x-axis here. And with these two ratios, we get areas of different classes. So we have tide dominance in the reds, wave dominance in the blues, and nonlinear dominance in the greens. So here is for uniform sediment coverage. We have spring high water at the top and spring low water at the bottom. And from left to right, we go from median waves to large to extreme. We see for the energetic conditions, the large and extreme waves, everything's in the blues, so it's wave dominated and these parameterizations should apply. Whereas for median waves, the parameterization should be used with caution because we're seeing a peak in dominance of the wave current interaction here. So it's the combination of the waves and the currents combining and interacting that's driving most of the sediment of the sand bypassing here. And here it is for non-uniform sediment coverage. So again, we have a larger peak in the wave dominance here, but we haven't got sediment with suspension by amplified currents off the headland toe because there's no sediment off the headland toe. But we also have, we still have that peak of nonlinear wave current interaction here in the median wave conditions. So wave current interactions had a very minor effect during the extreme waves, but they had the greatest effect for median wave heights, and there was a widespread, this isn't shown on these graphs, but there was a widespread activation of bypassing as well in some cases, particularly for median waves and in some cases for large waves. So to conclude, headland bypassing can be predicted. Predictions can be improved by accounting for the depth of the headland toe and the coverage of sand, particularly off the headland apex. Waves are the primary driver of headland bypassing. However, changes in tidal elevation modulate bypassing rates by changing that apparent morphology, which we can account for in the parameterization. And waves dominate bypassing for energetic conditions, but the wave current interaction can dominate for lower energy conditions, so medium waves in these macrotidal regions. The key morphological parameters to consider are the cross-shore headland extent, the depth of the headland toe, and the sediment coverage of the headland apex. So thank you for listening. I'm happy to talk further via email or on Twitter. Thank you very much.